Hello, my name is Ignacio Martínez Terés. I enjoyed a 3-month stay at Georgia Tech as part of the Marie Curie Rice Project, CoMetaS, that took place from October 2023 to January 2024. And in this presentation, I would like to talk about the work I carried out during that stay and its impact into the research done by me up to this date. To begin, I would like to introduce a little of my background, including my education and previous work experience. I completed a bachelor's degree in aeronautical engineering at the Universidad Politécnica de Madrid in Spain, equivalent to a current master's degree. Following the finishing of my studies, I obtained an internship position at the National Institute for Aerospace Technology, INTA, specifically in the Mechanisms and Structures area, within its Materials and Structures department. I spent 3 years in this position, and as my internship was coming to an end, I began working in the very same area at INTA as a predoctoral research trainee. This role in which I am currently in is connected also to my enrollment in the PhD program in aerospace engineering at UPM, which I started around the same time. As I mentioned before, from October 2023 to January 2024, I completed a secondment at Georgia Institute of Technology under the CoMetaS program. I consider that this 3-month research stay provided significant benefits to both my research and professional development. During this time, I contributed to work package number 5, specifically task 5.2, focusing on developing code to allow the dynamic characterization of metamaterial lattices. The results of my work were compiled into a report and this presentation, thereby contributing to the project and enhancing my communication skills. This experience is expected to have a lasting impact on my career, as the collaboration with Georgia Tech will strengthen my connections within the international scientific community, and the knowledge gained will positively influence my future research. Additionally, this secondment is going to help me to obtain an European doctorate mention. In summary, the secondment was a valuable experience that expanded my knowledge, improved my skills, and increased my potential for future collaborations and contributions to impactful research. So, I have mentioned that my work is related to metamaterials, but what are metamaterials? Metamaterials are microarchitected materials that can exhibit unique properties compared to the book materials that they are made of, properties that are mainly derived from their design structure. Metamaterials represent a fascinating class of porous structures that hold immense potential in engineering applications. These structures, often constructed with regular lattice, use repetitive unit cells as fundamental components to create intricate 3D forms. This repeating pattern of unit cells may enable, in some cases, the manipulation of mechanical waves. Within these unit cells designs, sometimes you find configurations with the struts and nodes that are arranged and interconnected throughout the three-dimensional space, and sometimes you find more complex geometries. It is important to note that varying unit cells designs give rise to a diverse range of structural properties, including some exotic ones that cannot be found on bulk materials. Among other vibration problems, one of the challenges in spacecraft design in which metamaterials can help is the issue of microvibrations. These are structure-borne vibrations generated by onboard equipment that can cause motion in the payload or other sensitive components, leading to performance degradation. Although this is not a new issue, it is increasingly being considered a problem due to the ever more stringent performance requirements of spacecraft payloads. These vibrations are typically in the range of micro-Gs and occur at frequencies from as low as 0.1 Hz to 1000 Hz. Common noise sources include reaction wheels, antenna pointing mechanisms, cryo coolers, social array drive mechanisms, and optical mechanisms. Microvibrations are studied separately from other mechanical vibrations because the associated requirements are not related to structural integrity, but rather to the stringent performance demands of the payload. One notable application of metamaterials is the mitigation of mechanical waves propagating through a structure. By analyzing periodic arrangements, it is possible to predict the frequency band gaps where wave mitigation occurs, known as phononic band gaps. This is achieved by constructing a dispersion diagram for a single unit cell with imposed periodic boundary conditions, as the ones that are represented here in this picture. This process allows us to characterize a specific lattice and compare different unit cells based on geometry or base material. In order to obtain a dispersion diagram of the unit cell of interest, for example the one that is represented here, it is needed to impose periodic boundary conditions on the finite element mesh of the unit cell. This is made by applying the Bloch theorem, also known as Bloch-Floquet theorem, that assumes a plane mechanical wave propagating along an infinite medium, in which the unit cell repeats itself infinitely. There is a problem with this condition. It imposes a complex relationship between degrees of freedom that a commercial FEM solver, such as Nastran, cannot manage. The solution is to study an equivalent problem in which we consider the real and the imaginary part of the solution as two different sets of degrees of freedom. In practice, what we do is to duplicate the mesh, consider one to be the real part and the other the imaginary part, and transform the Bloch conditions in our original problem into multiple constraints with real coefficients, which FEM solvers can manage without any problem. Applying the procedure exposed before to the unit cell considering a unidimensional problem and exploring different values of the variable k, which is the wavelength of the mechanical wave considered, it is possible to obtain the eigenfrequencies for each case and represent those frequencies in a graph like this, which is called a dispersion diagram. Taking into consideration our problem, the interesting parts of the dispersion diagram are the ones in which there are no eigenfrequencies for any given value of k, here represented in gray color. These regions are the so-called band gaps and indicate the presence of a band of frequencies in which the vibration are going to be mitigated when applied over a finite periodic arrangement of this unit cell, no matter the mode of excitation considered. It is not only possible to generate the data to build the dispersion diagram, but using pattern as a post-processor, it is also possible to recover the modes of vibration associated to each one of the eigenfrequencies. Here, you can see an example in the upper bandgap region marked in red, with a disk phase of the mechanical wave between opposite phase of pi radians. This means that in this particular mode, if you could visualize the infinite array of cells, you would see the same mode in all of them, but presenting the maximum at different times, with a difference in the phase of the wave of pi radians as the mechanical wave propagates itself through the medium. And this one, in the lower limit of the bandgap, also marked in red, has a disk phase of 0 radians between the opposite phases, which means that in this mode, all the cells in the infinite medium would move at the same time with the same harmonic movement. To summarize, Python code, specifically using the PyNastran package, was developed to generate unidimensional dispersion diagrams using Nastran software, aimed at characterizing metamaterials from a dynamic perspective to allow the identification of bandgaps in the unit cells and to identify and represent the modes of vibration of an infinite periodic lattice. The work done during this period lays the foundation for future advancements in analyzing vibration mitigation using metamaterials, such as the enhancements of the code to allow the generation of dispersion diagrams for bidimensional and three-dimensional lattices, and the future conduct of parametrical studies of metamaterial unit cells aimed to fit surrogate models. The study of the properties of a single cell of a periodic metamaterial, it is considered here as a previous step before considering its future application to non-periodic functionally graded metamaterials. It is also expected to publish a paper based on this work, supplemented by future actions. Finally, I would like to thank the European Union Horizon 2020 research program for the opportunity to carry out this secondment, and to Professor Kalidindi and his research group for his welcome and support during the secondment period. Thank you very much for your attention.